Okay, tell me what you'd like me to do. Okay, well, if there are no requests, I will do what I usually do in this situation, which is go through some old homework exercises. Okay, so what did you have last time? 4, 3, 5, 4, 1, and then 4, 3, 4, 5, 4, 6. Let me just check here. Okay. Okay, let's look at then 4, 3. So this was about absoluteness. So it's a matter of choosing what you want to say about it to give an adequate answer to this. X is regular are downwards absolutes from V to L. So deduce that if kappa is a regular limit cardinal, or just a limit cardinal, then it's a regular limit cardinal in L. So it's the usual picture about, you know, what happens between V and some class that's contained within it, right? W in general, is that if in V I've got some ordinal here kappa, and V thinks kappa is a cardinal, so kappa is a cardinal, this is equivalent to saying, right, for all functions f, if domain of f is some gamma that's less than kappa, right, then the range of f is not kappa. So there's no onto map from a smaller ordinal onto kappa. Now, if I've got functions here inside W, W may think, oh, kappa is a regular, kappa is a cardinal, because there is no map F inside here that takes some smaller gamma onto kappa. But that's not necessarily true in V, because there may be other functions inside V which do take some gamma onto kappa. But we're being asked the other way around. We're being told in V that kappa is a cardinal. So there isn't, for any function you take, it can't have a smaller domain than kappa and beyond to kappa. But of course, this includes all the functions that are in W. So it's quite natural then to then say, okay, this implies that kappa is a cardinal. In W here. As long as W is absolute about what is a function and what is an ordinal and so on, which is often why we say W perhaps should be a transitive ZF minus model. So all we're doing here is just applying this with, and the picture would have to be adjusted from V to L. L is then just, of course, get rid of the W, and this extends down to the bottom, right? So here you could then just say, right, as ZF minus and holds in L, and L is transitive, we can apply this reasoning. And there wouldn't be anything else to say about that. Okay, I hope there are no questions about that. Sorry, that's the wrong thing to say. Are there any questions about that? Okay, so this is about being a cardinal. So cardinals are downward absolute from V to L. Regular cardinals it's more or less exactly the same idea. Again, it's a pi1 question for all functions f, right? If now domain of f is some gamma less than kappa, right, then the supremum of the range of f is not kappa. So I'm saying I can't have a map from a smaller gamma than kappa cofinally into kappa. So another way of putting this is saying for all functions f, if the domain of f is gamma, it's less than kappa, right? Then f is not cofinal into kappa. Which is equivalent to saying that kappa is its own cofinality. This is what regular is. Eh? Of course, it's a little bit hard to unpack then, because you have to say what cofinality means. Well, it's this here. Eh? So this is the basic description of being regular stated in terms of cardinals. There's no map from a smaller gamma cofinally into kappa, unboundedly into kappa. But again, these properties here, these can all be expressed in a delta zero fashion. So just to elaborate a bit more. So these things here, these are all definite anyway. So absolutely definite. And the same will be true in the stuff inside these square brackets here. Right? So this again is, so this is absolute for transitive ZF minus models. And again, there's a for all quantifier outside. And for the same reasons as here. Right? If there are no functions in V from some gamma less than kappa cofinally to kappa, there certainly aren't any L. So then you could just say, so just as above, kappa being regular implies that it's regular in L. I mean, indeed, for an answer like this, it's almost enough to say that kappa is a cardinal, can be expressed using a pi1 formula, and therefore it's downwards absolute from V to any transitive ZF minus model. So just the syntactical form of the formula is enough to guarantee it's absolutely definite. Sorry, it's downwards. Sorry, that's wrong. It's enough to say that it's downwards absolute to transitive ZF minus models. And likewise for regular. So the last part just says, deduce if kappa is a regular limit cardinal, it's a regular limit cardinal in L. Well, we've got the regular part being downwards absolute. It's just a question of being whether, if it's a limit cardinal in V, it's a limit cardinal in L, right? But again, this is true for the same reasons. Kappa is a limit cardinal, right? If and only if for all alpha less than kappa, there is a lambda that's less than kappa, where alpha is less than lambda and lambda is a cardinal. So again, the picture would be, here is kappa. Kappa is a limit cardinal. Any alpha I pick, or you give me, then I can find a lambda that's bigger than alpha, which is a cardinal. And that's in V. But I know being a cardinal, by what we've just reasoned, is downward absolute to L. So actually, any of these cardinals in V are also cardinals in L. So what is true in L? For any alpha less than kappa, there's a larger lambda between it and kappa, which is a cardinal. Being a cardinal is downward absolute. From V to L, kappa must be a limit of cardinals. This holds in L too. So kappa is a limit cardinal in L. So actually, there's not an awful lot to say then about that part. Actually, one of the things that's of great interest to set theorists is L. What one has is that one may have limit cardinals in V. So kappa may be singular. Right? So it's a limit cardinal in V. But that doesn't rule out the possibility that it's actually an inaccessible cardinal in L. So lambda may be a singular cardinal, and hence a limit. Whilst being regular in L. And actually, there's quite a lot you can say. If singular cardinals in V are regular in L, then we know that V is not L, but in a very dramatic way. Of course, we know that V is not L because in V there would be a function cofinalizing lambda, which is absent from L. So I know the things that are in V were not L, but actually, in that case, and I mean, it would be going too far afield to talk about it, we know that L looks almost like the ordinals. It becomes terribly thin. So V is not L in a big way. L looks like just the ordinals. I mean, it is something of an exaggeration, but I mean, here would be V, right? Here would be the ordinals. And L suddenly looks terribly thin if this happens. I can't draw it very well. There's an awful lot of stuff outside of V. And in fact, there end up being sort of automorphisms of L if there are singular cardinals of V that are regular in L. So L ends up as being non-rigid in this case. It has automorphisms. That's not quite the right thing to say, but I'm just using an algebraic word there. Notice the other thing is that, of course, regular limit cardinals in L, which I mentioned last time with doing one of the other exercises, are always strongly inaccessible in L. If kappa is a limit, if kappa is a regular limit, cardinal in L, then it is strongly inaccessible. Being a regular limit just makes you weakly inaccessible. But strongly inaccessible means you're closed under the power set operation, right? And this is because the GCH holds in L. And the GCH says a weakly inaccessible cardinal must be strongly inaccessible. If kappa is weakly inaccessible, then since 2 to the lambda is always lambda plus, which is less than kappa, for any lambda less than kappa, this means the size of power sets of anything, any lambda less than kappa, is still less than kappa. So kappa is strongly inaccessible. So if this still seems mysterious to you, okay, go away and review what the GCH is saying and what the definitions of weakly and strongly inaccessible are. And as I said last time, this meant in ZF, C, we can't prove the existence of a weakly inaccessible cardinal because that would mean that kappa was strongly inaccessible in L. and therefore there'll be a model of ZFC in L. And that will contradict Gödel. Okay, any questions about that one? Then? Okay, what else did we have there then? 4-5. Show the order type of L kappa under this less than sub kappa. So this was the well order of L kappa that we defined in the proof that the AC held in L. That this order type is kappa for kappa and infinite cardinal. So the order type of, so you look at L and you look at the global well order of all of L. This is OM. So recall that less than sub alpha was the well order of L alpha defined in the proof of AC holding in L. We did. Well, the fact that this order type is exactly kappa comes out of our calculations on the sizes of the L alphas. It kind of spins off our calculation on the sizes of L alphas. So what do I mean by that there? So recall that we showed the cardinality of L alpha is the cardinality of alpha for any ordinal. In particular, if kappa is a cardinal, then of course then cardinality of L kappa is just kappa. Right. But L kappa is the union of the L alphas. Right? This is what happens at limit stages. Moreover, we had that if alpha was less than beta, then not only was this ordering a subordering of this one here, but this ordering was an end extension of this one. So, if this was L beta, and here is L alpha, we've got this ordering of L alpha and the ordering of L beta is just continuing the snake up here. we don't reorder things so that some new set up here gets before some old set that's down here. So if I were to draw the snake out in a line, what I'd have here is, I mean, here might be the ordering up to L alpha. And then here's the ordering up to L alpha plus 1. It's just getting longer all the time. Here's the ordering up to L alpha plus omega. So this is just getting longer and longer and longer. And each of these initial segments can't be shorter than the cardinality of L alpha here, because it includes all the elements of L alpha written out in a long line. So this line can't be of smaller cardinality than of L alpha itself. The order type of L alpha with this ordering cannot be less than the cardinality of alpha, because the ordering here will be a bijection between L alpha and whatever this order type is here. But then that will be a bijection between this cardinal and something smaller than it. In particular, the order type of L kappa is not less than kappa. Again, if you wanted to give a reason in words, as L kappa has kappa many elements. Right, so this can't be shorter than kappa. We'd have an enumeration of kappa many elements in by some ordinal less than kappa. On the other hand, we'll show that it's not bigger than kappa. The order type of L kappa here is not bigger than kappa. Suppose this were larger than kappa. And in this ordering, there were some objects that were placed beyond the length kappa when they were run out, when I unraveled the snake up here. Because otherwise, so there's some element of L kappa, U say, which would be the kappath element in this word ordering here. It would be some element U say of L kappa, where I could look at the ordering on L kappa and I could restrict it to the elements that come before U. Restricted to the elements earlier in the ordering than U. Right, so here's L kappa all laid out. And we're supposing that this snake here, this ordering is longer than kappa. So there's a kappath element here. So U gets placed on this ordering here. So there are kappa many elements before U, and then there's some more, supposedly, coming on at U or afterwards. But U sits inside L kappa, so it's in one of the L alphas. For some alpha less than kappa. Right? I don't think you have to spell it out, but since again we're using L kappa as the union of the earlier things. But now what does this mean? This is the contradiction. Less than kappa end extends less than sub alpha down here. So everything that comes before U is in L alpha. Everything that comes before U in the ordering is also in L alpha. Because it's an end extension, the snakes extend each other here as they get longer and longer. But that means that L alpha has kappa many elements, which is too many, right? Because the cardinality of alpha is less than kappa. So, but this would imply that the cardinality of L alpha is kappa, or is greater than or equal to kappa, which is a contradiction. So it's not the case that this order type is strictly bigger than kappa. Right? So the only thing left is for it to be kappa. It's precisely kappa. Any questions at this point? Okay. Where are we? So I've lost the question. It also asked about the order type of the whole ordering. So the idea is, well, the picture is, of course, ON, perhaps it looks a bit like an infinite cardinal. So this picture is kind of the same as this picture. I mean, one could have well orderings that look a little bit longer than the ordinals, right? I mean, I'll just say something about that in a moment. So I think you say something like this, the same reasoning. That as the ordering of L is just the union of these, right? Any U in L, if U is in L kappa for kappa cardinal, what we have is the predecessors of U have size less than kappa. They are a set and of cardinality less than the next cardinal. And of cardinality less than next cardinal above the L rank of U, wherever U occurs in the L hierarchy. So the L rank of the set here. So in this picture, if I were to put here the ON for the top of the ordinals here, it would be saying that the ordering of L doesn't stretch out beyond the ordinals in some kind of magical way, because any U that's in L is really in some L alpha. So its predecessors form a set. Right? They can't be a larger set than the size of the next cardinal kappa. Down here. So I think that would finish that one here. I mean, you might be asking yourself, I mean, well, surely I can't have well orderings longer than the ordinals. I mean, what's longer than the ordinals anyway, right? But it is possible to define class terms that define orderings that are not set-like. So this is a bit of an aside here. So an ordering AR here is set-like. If you look at any predecessors of an element A in here, its R predecessors form a set. So if only, let's say, little b here in A, the initial segment of A formed by B, this is supposed to be the element C in A such that C comes before B. Here, this is a set. So what we've just argued is that the well ordering of L with its global well order, this is set-like. So we've just argued this. But there's nothing stopped, just as you can take the, the even numbers, and you can put them before the odds. And this gives you an ordering of the type omega plus omega, just out of the natural numbers. Well, actually, there's nothing stopping you defining that ordering, extending that to the ordinals. I could just put all of the even ordinals, which includes the limits, omega plus 2k, and in general, some kappa plus 2k, where k is less than omega. I could put the even ordinals before the odds. And now omega is not in there, but omega plus 1 is in there, and omega plus 2k plus 1. And in general, something plus 2k plus 1, k less than omega. I could imagine a picture that's like this, followed by this. And if I were to think about what the order type was, the only thing I could write down sensibly is that it's of the form ON plus ON. I put all, there's ON many even ordinals, and then I put ON many odd ordinals here. So this is not set-like because there's a proper class of even ordinals beneath 1 in this ordering. Then this ordering here is not set-like. Okay. So any odd has a proper class of earlier elements. So it is possible to define orderings, will orders even, that are longer than the ordinals, right? But a will ordering is not the same thing as an ordinal. We've got a theorem that says that every well ordering is isomorphic to an ordinal. Actually, if you stated that more carefully, what you'd have is that every set-like well ordering is isomorphic to an ordinal. This is a non-set-like well ordering that's not isomorphic to an ordinal. It's too long. Okay. So let's see, what else have we got? 4-6. Suppose there is a transitive model of ZFC. So better to have put this is to say there's a transitive set model. That's what we really want here for this to be quite clear. So there's a set that's a transitive model of ZFC. Show that there's a minimal model. That is, for some countable ordinal, beta 0, ZFC holds in L beta 0, and that L beta 0 is contained in, let's say, M. Where M is any other. And now I did remember to say set model of ZFC. So the idea here is this L beta 0. And the idea is that any other set model here, or perhaps it's a taller one, like this, contains this one. So it's the kernel of any other set model of ZFC here. So we're told there is a model. So let M be transitive. And it's a model of ZFC. So, in fact, M epsilon is a model of all the axioms of ZFC here. So We get another sheet of paper then. We're going to use the Löwenheim-Skolem theorem to say M has got a countable substructure here. So, since M is a model of all of ZFC, we have that L, in the sense of M, is L up to whatever the ordinals are in M. So here would M be M. It's a set model, so it doesn't have all of the ordinals in, but it's L, because it's a transitive ZF minus model, its L, in the sense of M, is just L up to as many ordinals it's got. So we had a lemma that told us this. But M is a model of ZFC, and we proved in ZFC that L is a model of ZFC. So we're going to have that, as we showed in ZF, that ZFC held in L. So we're going to have that M with epsilon. This also thinks ZFC holds in L. And, well, what is its L? It's the ordinal height of M. Hence, ZFC holds in L theta, where theta is the height of M. Right, so that's the ordinals there. So that's the first observation. If I've got a model of ZFC, its L is a model of ZFC. Okay, so now we know something more. There's not just set transitive models of ZFC, there are levels of L that are models of ZFC. Now, by the downward Löwenheim-Skolem theorem, there is some X, which is an elementary substructure of L theta, with X countable. Right, so we don't know how big this theta is, but there is this X down here, consisting perhaps of these scattered sets. Maybe there's a transitive part to X, maybe there's this other stuff here, but it's countable. By the condensation lemma, right, X is actually isomorphic to some L gamma. Okay. Because this is a model of all the axioms of ZFC, so is X, so is L gamma. So and hence ZFC holds in L gamma. But gamma is countable because X is countable. So now we've reduced our L theta, which is perhaps an uncountable model of ZFC. I found a countable model of ZFC. The question asks for a minimal such. Well, I just look at the ordinals. The ordinals beta says that L beta is a model of ZFC. And I let beta 0 be the least of those. So let beta be 0 be the minimum of those betas less than omega 1, such that ZFC holds in L beta. I know the set is non-empty because gamma's in there. So this smallest ordinal, where we have a model ZFC, is the thing that we're going for. L beta 0 is this minimal model. Of ZFC. And you might say, oh, well, why is it minimal? Because for the reason we just had up there, if n is transitive and ZFC holds in n, as above, we have, right, L in the sense of n is a model of ZFC. So L beta 0 is going to be possibly an initial segment of this, L in the sense of n, which is contained in n. Which is why this is the minimality that we were after. It's contained in every other transitive model of ZFC.